Hey, okay, welcome back to the second episode of High Stakes Mathematics, where we try and save the planet with very rigorous computer checked mathematics. Last time I was looking for this definition inside the Proof Explorer, and I found it, so I thought I'd have a little play around with it. And what df_dec_10 does is it defines this semicolon notation for semicolon with two things after it, and it shows you that it's 10 times a plus b. Right? So let's just have a look. So if I get out a new theorem here, and I say, I don't know, maybe I'm trying to prove 5 equals 6, which is going to be a bit of a challenge. But let's say 10, I say df_dec_10, okay? Okay, it doesn't like this. It's saying there's grammatical errors. I think that should fix that. Okay, so it's offering me two slots, and it's saying I've got a slot here, this is what was A, and a slot here for B. And then if I put this in, what I'm really doing is I'm having C1 and C2. So for example, if I put in 1, that fills it in there. And if I put in 2, that fills it in there. So what that's saying is 12 in this semicolon notation is 10 times 1 plus 2. And because 1 and 2 are well defined in the database, then we can work with those operations. But it is also true that I can use this in a nested way, right? So if instead of C1 here, if I said, okay, I'm already at 34, okay, that's what I'm replacing C1 with, and then C2, I'll replace that with a 7, then I get 347 is 10 times 34 plus 7. And you can see how that's quite clever. So with this semicolon notation, you can like sort of build up from the inside. So really what this is it's semicolon 34, which is then semicolons with 7, right? And semicolon 34 is semicolon 3 with 4, right? So you can sort of nest up these larger digits, which allows these simple theorems to be proved for everything you need all the way up the tree. Okay, so let's get rid of that. And let's start again. So the aliens turn up above the planet, and they're like, we're going to destroy another city. I don't know why they speak English. That's a pretty big science fiction convention that aliens always speak English. And they say, unless you can do some, we're still on arithmetic. We haven't got very far with this. Subtraction. Oh no. Can you do 9 minus 2? That's it. You know, this is the grand challenge they present us. So let's see if we have 9 minus 2 equals 7, I would have thought it would be. Okay. It doesn't seem to be in the database already, which is interesting. Let's search Google to see if that can find it. Metamath 9 minus 2 equals 7. Doesn't seem to think it's there. That's really interesting. Yeah, okay. So I think probably this isn't in the database already. So let's try and do it. New proof? No. Theorem label? I could give it a good name if I wanted to, but I think it's easier just to start with something like that. So it was 9 minus 2 equals 7. So one thing I might try, and this occasionally causes metamath to crash, is just put an exclamation mark in there and say, can you just do this for me? No. So sometimes it's able to jump to the end and just say, okay, yeah, I can find some theorem in the database that proves this for you, but I'm pretty sure this is not already proven. So what are we going to do? Okay, well, one suggestion I have is working with minuses. There's probably less theorems that deal with negatives in the database and subtraction than there are with positives and addition. So maybe one thing that would be helpful is I could put in a line here and I could say 9 equals 7 plus 2, right? So I can transfer this 2 over to the other side. Let's see if it's happy with that. Okay, so interestingly, metamath says that this is too big of a jump. It can't get straight from here to here. And I think any other mathematician would accept readily, yeah, if you have 9 minus 2, 7, you just do the same thing to both sides. But metamath is going to need some intermediate steps. And so if I do 120, I do 9 minus 2 equals 7 plus 2 minus 2. Okay, so that's really what I'm doing, is I'm saying, okay, I'm doing the same thing to both sides, right? And let's see if you can fill that in for me. Yeah, so it's saying, we looked at the overkill theorems last time. It's that one where if you do the same thing to both sides, it's happy, right? So it's happy that these two things, this is the same, this is proven from this. If this is true, then that's true. And like one of the things with overkill theorems is that you can like heavily abuse them. So if I say if I say 5 equals 7, and then I say 5 minus 2 equals 7 minus 2. Metamath will fill that in for me with overkill, and it will say if 50 is true, then I'll let you have 60, but 50 is false. Obviously 5 is not equal to 7, but that's not the point that it's making. Like, metamath checks everything on these atomic little steps. So it says the step from 50 to 60 is valid, but the step 50 is not. Okay, so same here. I don't know if 9 is 7 plus 2 yet, but I do know that if it is, then this step is okay. All right. So then it's now also saying this is too big of a leap to get from here, so it can't figure that out. So how about we take this right-hand side, and can I jump straight away to that being 7? Is it happy with that? Yes. Okay, so it's found this nice theorem for me, Pn can 3oi, which I guess is like, the can is probably for cancel, right? And it's saying that anything plus, something plus something minus something, if those two things are the same, it's equal, right? So it's filled that in for me, which is great. And it's also filled in the last step, because it's saying, okay, these two things are equal, and these two things are equal, and therefore this is equal to that. Okay, so that's what it's done with xtree. I can probably show that more clearly. So it said, we have this first one, A is equal to B, and B is equal to C, therefore A is equal to C, right? So that's kind of what the try is in there, that it's three things linked together, equal of three things together. Okay, making progress. So we now need to just show 9 equals 7 plus 2. So what if I started with df9? Is that a good place to go? Let's see what that is. So 9 equals 8 plus 1, right? And what about if I brought in df7? Okay. Oh no, sorry, I think I'd rather have df8. Would be good to have here. Okay. Can you figure it out from there? Yes, done. Proof generated. Right? So ironically, it's managed to put the amazing step of 9 equals 9 in, so that's good. But, it's important to check everything. And so then it's managed to say 7 equals 7. Oh, it's got this. We could have just kind of used that as a much shorter shortcut. 7 plus 2 equals 9. That would have given us, and then you flip that around and that gives you 9 equals 7 plus 2. So a lot of this is wasted, actually. Once you've got, I think if I delete this and then put that like that, I think that will be enough. Yeah, so that's simplified the proof, right? And that's a good example of how there's lots of different ways to construct a proof. You can add a lot of like erroneous steps and things. And the more elegant proofs in the database are the ones which have less steps. And so by deleting that, we managed to just start with 7 plus 2 equals 9, so therefore 9 equals 7 plus 2, and then we use this little bit of logic there. So we get 9 minus 2 equals 7, and we proved it, which is great. So we've got this metamath proof. So we've got a machine-checked proof that all the way down to the set theory axioms, to the ZFC axioms, we do believe this is true. So let's fill it in. Let's risk our planet. Let's risk our city on 9 minus 2 equals 7. Correct. Okay, good. So the city hasn't been destroyed yet. And let's see if they boost us up to advance. Okay, and one of the things I wanted to... what is 73 less than 688? Okay, well, let's try it. So 688 minus 73. Any proof? I do not want to save my changes. The theorem label will be this. Okay, QED. So let's use the semicolon notation. So as again, as I talked about, that's semicolon 68 times 10 plus 8, and that's semicolon 6 times 10 plus 8, right? Minus, let's check this right. What is 73 less than 688? So minus 73, 73 equals, I reckon that is 615. Right, because 615, you add the 3 on at the end, you get 8, and you add the 7 on, you get 8. I think that's right. Okay, but we're going to check it, and that's what's going to help. Is once we've checked it, we'll be highly confident that's right. Okay, so it can't find the solution for us yet. And I think maybe there's two strategies I can think of for this. One is to use a thing called dec sub, which is about decimal subtraction, which is probably going to work. And the other is, a bit like before, to move the 73 to the right-hand side and then use dec add again, because that seemed to be quite easy last time. So let's try dec sub. Let's see if we can get that to work. Dec sub 1, dec sub I. Let's try that. Okay. And then let's just bung this in and see if we can kludge it together. So that's what we want to prove. Okay, it's got pretty far for us. It's got 6 and 1, and it's made this 61 compound, and then it's got 7 and 3, it's made the 73 compound. And it's then saying 6, 8, 8. Yeah, see, this is not going very well, because 6, 8, 8 equals 6, 1 something. I don't think there's anything you can put in there that's going to finish that off. And then something minus 73 is 5. 61 plus 1. I mean, I can try filling it in and we'll just see what happens. 62, I assume that's got to be. And then this is going to have to be 78. But that's not proven. And again, look, it's kicked up this line, which is 8 minus 78. That is not going at all well. We're going to really... And 8 equals 1? Okay, so this is not going well. I wonder why. It's an interesting question, isn't it? Like, what is the problem? Dec subby. 668 minus 73. Because you'd think you don't need a carry or anything. I think there are theorems that have carry in. This is often quite a good trick with metamath, is to search for the theorem itself, dec sub b. Okay, and then search nearby theorems, and you can have a look around. So see if there's anything else. So dec mul, that's probably going to be useful later if we want to multiply them. Dec addy ci2. And I can search in this page for sub. It's literally only got one theorem. Okay, that's not giving us a lot of options there. All right, let's try proof strategy number 2. The future of the world hangs in the balance. Let's try moving things to the other side, right? So let's just check that's okay. So let's I want to take this and I want to put the 73 on this side. Okay, so I'm hopeful that that's going to make it a lot easier, and then we can just work with addition, right? Similar trick to what we did before. Ooh, hello. It liked that. It liked that a lot. Yeah? Has it filled it all in? Wow, okay. So it knew to use dec add, right? And then it built up 68 is 61 plus 7, 1 plus 7 equals 8, 7 plus 1 equals 8, and it filled in all these steps. It was really very clever. Huge props to the people who made MMJ2, which is this proof assistant, because to have filled all that in, this is a lot of steps it's managed to do by itself, which is really impressive. But the only thing it can't do is jump from there to there. It's not very good at algebra. So let's help. That's what I'm here for. Got to pretend to do something. Can't take all the credit for saving the Earth when I haven't actually done anything at all. So let's do what we did last time. We'll have this, but we will take away 73. And we will have this, but we will take away 73. Like that. Okay, good. And then, same as before. And I think this is quite a good example of working with metamath. Of like, it's nice to try a simple problem, like what was the first one we tried? 9 minus 2 or something. And now we're doing it with larger numbers, but we kind of got the same proof techniques in our head, which is really good. Okay, and then I wanted this is equal to 615, I think. 615. Formula contains an error. Okay, so you can't have brackets around here. Metamath is very particular about notation. Like if you get the notation wrong in any way, it will be very upset with you. So you have to get it exactly right. Ooh, okay, I did it. Amazing. Well, I say I did it. I think the people who worked were incredibly hard to build a metamath database, and the people who built MMJ2 mostly did it. I just did some fiddling around with it. But there we go. Proof generated. So it's formally proven for us that this thing is right. So this proof strategy of starting with the subtraction and then transferring it over to be an addition problem, right? So we went up to here, which was 688 equals 615 plus 73. That helped quite a lot. And I think even in the Middle Ages and the Renaissance, there was some problems around, it was either negative numbers or complex numbers or something, where they didn't like writing polynomials with negatives, so they'd sort of move the terms over to the side where everything was positive, and they'd sort of always keep trying to shuffle their equations around so everything was positive the whole time, which is really interesting because they weren't very comfortable with negative numbers. But it seems that with these deck things, subtraction, I could only find one theorem. I'm sure there's more, but I just don't know the database very well. So yeah, okay, let's put it in. So 688 minus 73 is 615. Okay, let's see. We're risking Jakarta. Correct. Okay, good. So that city won't be destroyed quite yet. All right, and that seems like a good place to end the episode. So tune in next time for some more exciting mathematical problems like 23 minus question mark equals 2. Although we might have to move on next time to the next level, which I think is going to be multiply. So that's a whole nother step up of complexity. So there we go. Hope that's been fun. Hope it's been interesting. See you in the next one. All right, bye.